Hey, chemistry team, it's your chemistry coach coming at you for video number 9 for complex ions and coordination compounds. This should be the last video of this series looking at the colors of complex ions, which is like we've reached the pinnacle, the top, the cool stuff, but we needed to learn all that other garbage so we could actually predict colors of complex ions, or if we have the color of a complex ion, why. You know, theoretically, be able to explain something. Why is that yellow? Why is that purple in solution? Why is that solid blue? All right, so we got some review, a little bit of review concepts to look through. You know, looking at color, the color spectrum, and a little bit of quantum mechanics. So let's start with this. If we're looking for the colors of complex ions, we need to understand one basic factor, right? The crystal field splitting that occurs, whether it's octahedral, tetrahedral, or square planar complex, that splitting of the d orbitals due to the presence of those ligands, that energy difference, right, that crystal field splitting happens to fall in the energy range of the visible region of light. So the visible region of the electromagnetic spectrum, right? You got visible, infrared, ultraviolet, X-rays, microwave. This falls in the visible range. That's why they're such cool colors. Yay! Right? If it doesn't fall in if the energies don't fall in the visible range, then you just get colorless species. So most of the solutions of alkaline metals, alkaline metal ions, alkaline earth metal ions, they're kind of boring, right? They're all colorless, So we love these transition metals and the lanthanides and actinides. They give these really cool things, right? Here we go. Now remember from quantum mechanics, if the energy difference between the levels, right, this crystal field splitting, this is just an example of octahedral, where you got the dz squared, dx squared minus squared, y squared on top, dxy, dxz, dyz on the bottom. That's splitting in an octahedral complex, regardless of the complex. If that is an exact match of a photon coming in, so if we got a photon of electromagnetic radiation coming in, boom, and that photon has an energy that exactly matches that crystal field splitting, that electron can absorb it and go boink, and it can pop right up to that next region. Right, so this would be excited. So that would absorb a photon coming in, pop up here, and that photon would have an energy range in the visible region of light. Nice. And because of weak field and strong field ligands, this crystal field splitting can vary, which varies the different colors. So you just you put 6 different ligands on the same metal ion in the same octahedral complex, you could get 6 different colors depending on if they're different as far as the strong or weak field ligands. That's pretty neat. Right? And then if you do the same ligands, but you do an octahedral, remember, tetrahedral is about 44% of that. So if it was in a tetrahedral complex, that energy gap is going to be smaller by more than half. So that means the energy of the photons it's going to be absorbing is lower. If the energy is lower, that means the wavelength is bigger. See, they're inversely proportional, so lower energy would be a higher wavelength, more towards the 700 nanometers or something. But if you had a big gap, it'd be in the higher energy, in the 400 nanometer range. So what I want to do is just redo that spectrochemical series and relate it kind of in a rough way to the wavelengths of the visible light region of the electromagnetic spectrum. And this is just a rough rule of thumb to give you an idea of what colors things are going to be. So let me pop that up real quick. All right, gang, so I wrote kind of a condensed version of that spectrochemical series back on. I took out some of the weirder ligands out of there. So we got the cyanide, the nitrite, ethylene diamine, ammonia, some of the more common ones in there, but I left quite a few out, so it's more extended than it actually is. And again, what I'm going to do is just kind of a rule of thumb if you're trying to guess what color a particular complex ion would absorb. Okay, and we'll have to talk about subtractive color mixing in the next board, which should be pretty tough on a board. Remember, the crystal field splitting is equal to the photon energy that's absorbed, which is based on Planck's equation, is inversely proportional to the wavelength. So the higher the energy of the photon, the lower the wavelength, and vice versa. The lower the energy, the higher the wavelength. So I want to get across, what I'm going to do is look at the color region. And remember, visible light, Roy-G-Biv, red, orange, yellow, green, blue, indigo, violet. Red being lowest energy, around 750 nanometers or so. and violet being around 400 nanometers, give or take. You know, there's no set numbers there. So let's take a look. These strong field ligands create a high crystal field splitting. The weak field ligands create a lower crystal field splitting. This would be for an octahedral complex. Higher crystal field splitting means higher energy photons absorbed. Smaller crystal field splittings means lower energy, right? If that's lower energy, it requires a lower energy here. And again, lower energy would be higher wavelength. So let's put that here. Lower energy would be higher wavelength. Higher energy would be a lower wavelength. So it's kind of the reverse of Roy G. Biv. Or, no, I can't do that. It's like trying to do the alphabet backwards. Like, I can't even do that sober. right? Okay, never mind. No stories. Here we go. So let's take a look at the reverse of Roy G. Biv. I'll do this in black. So things around here with a small crystal field splitting would be absorbing lower energy or higher wavelength in the reddish range. Right? So right around there, kind of those, the halide ones absorbing in the red. And then red, orange, yellow, Roy G, green, blue, if I could spell, indigo, Roy G. Biv. Whatever indigo is. Right? So you can get a rough idea, and you know, give or take, there's a lot of other factors involved, but just as a rough rule of thumb, you could kind of say, hey, you know what, based on the weak field, strong field ligands, at least in an octahedral complex, these are probably going to absorb in the reddish region around 700 nanometers, 750. Over here, you know, is the 400 nanometers. So we're going 400, 450, 500, 550, 600, 650, 700, 750 across like that. So here you've got increasing wavelength but decreasing energy. So a little review from last semester, first semester general chemistry. You might want to review your electromagnetic region and the visible region and the different types of colors. But it gives you a rough idea, and we can use this as a guideline. And what we're going to look at the next board on subtractive color mixing. If something's absorbing in the orange range, it's going to pull that out, and you're going to see everything left, which is the complementary color. If something's absorbing yellow, so white light's coming in. If something takes out yellow, you're going to see everything left, which is the complementary color. If something's absorbing blue, you're going to see the complementary color of that, right? As it passes through the solution, it takes out that yellow or whatever, and you see what's left. Subtractive color mixing. So let's take a look at that on the next board, but we want to know the complementary colors. Let's get some color wheels. I don't have enough color pens, so it's going to be a little weird. All right, you ready to review your complementary colors? It depends if you're doing additive color mixing or subtractive color mixing. We're going to be dealing with subtractive color mixing when we're thinking about, like in a laboratory, we pick up a bottle with a solution and go, oh, this iron 2 nitrate solution is yellow or something like that, or this cobalt solution is this color, or this copper solution is blue. Why is that? Well, it's because white light is traveling through, going through that bottle with the solution. The complex ion is absorbing very specific wavelengths, right? Very specific wavelengths equal to the crystal field splitting. And then the rest go through. So if I'm holding this bottle, the light's coming through, specific wavelengths get absorbed. What comes through? The combination of all the wavelengths that come through and hit my eyeball is the complementary color, right? Or if it's a solid or something, right? Or sure, the white light's coming through, boom, it hits Deadpool's head. The chemicals in there are absorbing specific wavelengths. The rest of the wavelengths reflect off. The complementary color is what we see. So we see this red here because it's the complementary color of what's being absorbed as the light's reflecting off. So, and what you get with subtractive color mixing, the primary colors would be yellow, which is a mixture of red and green, cyan, which is green-blue, and magenta, which is red-blue. Who comes up with these names? And then the secondary colors would be blue, red, and green. So if something's absorbing in the yellow region, we would probably see bluish. You know, I'll show you the color wheel for that, show you how we can see it. Now for additive color mixing, these are flipped, right? The secondary colors become the primary colors become the secondary colors. That's neither here nor there. All right, and just remembering, as white light, which is all wavelengths, are all colors, passed through, let's get my verb tense right, passes through a solution or is reflected off of a solid. Specific, I need spell check for a whiteboard. Specific colors are absorbed, right? Equal to the crystal field splitting, which varies with the ligand and octahedral and tetrahedral. The light transmitted, or what we see, is the remaining combination of all the wavelengths, or what we call, that's what the complementary color is. So what I'm going to do is attempt to put a subtractive color wheel up here. You know, I have limited colored pens, so I'll do the best I can. If I don't have the color of that specific pen, I will go ahead and just write with the first letter of that in there, and we will have that. And once we have that, we'll do a couple examples, think about it, and we'll be able to explain why a specific complex ion or coordination compound has a color, has the color it is, or do our best guess at predicting the color it would be. It's easier to know the color, and then we will know the complementary color and explain why. Because it's fuzzy with the spectrochemical series, weak and strong field ligands. There's a lot of gray area in there. I gave you a rough idea to tell whether it would absorb red or violet or indigo, those kinds of things. But that's just a rough rule of thumb. It's not very specific. So much harder to predict a color than it is to be given a color and explain why. So let's pop this color wheel up, my friends. Okay, gang, subtractive color mixing. This is kind of your wheel. It's opposite additive, right? So a lot of people think, like one of my 13-year-old daughter came in and she was confused by this. She's like, well, aren't red, green, and blue your primary colors, which is what you learn. But see, that's additive color mixing, like mixing paints. You know, if I mix red with blue, I get this color, I get green, right? That's additive. In chemistry and lab, we're looking at subtractive color mixing, right? We got a solution, white light comes in, certain wavelengths get taken out because of the absorption from the crystal field splitting, and we see what's left, which is the complementary color. Some subtractive mixing, the primary becomes secondary, secondary becomes primary. So now your primary colors are yellow, cyan, and magenta. Now, I did not have a yellow marker pen. That's the closest I could get to yellow. Imagine, with your great infinite imagination, that's yellow, right? So we've got cyan, magenta, green. So if you take cyan with magenta, right, you see the blue, you see yellow, magenta, you see the red, cyan, yellow, green, you see the secondary colors in here, and black. So if I take out all colors, that's black, right? So where all three of those primary colors overlap, and if you take out cyan, yellow, and magenta, you're effectively taking out or subtracting all wavelengths, all colors. There's nothing left. That's why it's black in the center, okay? So in essence, what we're going to do, looking for the complementary color, if something absorbs blue, right? Something absorbs blue based on the spectrochemical series, the crystal field splitting, we say it's probably going to absorb bluish, what is that, 400, Roy G. Biv, 500, 550 nanometers, something like that. So if blue's taken out, you see the complementary color, yellow. Imagine that's yellow, right? Or let's say magenta, right, is taken out. That color magenta is taken out. You'll see the complementary color green, right? If red's taken out, you'll see the complementary color cyan, right? So you can see the complementary colors, right? If this is taken out and that's taken out, you see the result of that. So all we need to know is what's its complementary. Blue complementary is yellow. Red complementary is cyan. Green complementary is magenta. So keep that color wheel. There's better pictures in your textbook. There's some pictures in your textbook with actual color pictures that show additive color mixing and then subtractive color. So take a look at that. Keep that in mind. Let's do a couple examples and see if we can predict some colors or explain some colors. Almost done with this chapter, baby. Example number 1. Let's predict a color. So we've got this complex with cobalt with 6 waters. So this will just be like a solution of, I don't want to tell you the charge, but hopefully you can figure out the cobalt's a +2 in there. So a solution of, say, cobalt-2 nitrate. You pick that up in the laboratory. It's going to have a color to it. Let's see if we can predict what the color, close within a, a region of the color spectrum. Like Roy G. Biv, if it's orange, I'll kind of take one before and one after that. So remember, we would just write that as cobalt-2 plus aqueous, but it really has the water ligands stuck to it. So go through coordination number, oxidation number on the cobalt, number of d electrons. Is that water a weak or strong field ligand? And then do me a favor and draw the crystal field splitting. Put in those like we did for magnetism. And let's figure out roughly what wavelength that an electron going from the lower d levels to the higher d levels would be, give or take, where that is on the spectrochemical series, right? And then what wavelength and color that would be on the color wheel, and then pick its complementary color. I'll give you a second there. I'm not going to pause it this time. Here we go. So we've got 6. So that's going to be octahedral. All right, 6 is octahedral. Oxidation number, these are neutral, so the cobalt's a +2. So the number of d electrons, so let me look up cobalt again real quick. And it's a +2, so cobalt's here, 1, 2, 3. Let's see, cobalt, 1, 2, 3, 4, 5, 6, 7. So it's going to lose these 4s electrons, give you a 3d, 1, 2, 3, 4, 5, 7, 3d7. Okay? So it's got 7d electrons. So that's going to be argon 3d7. Water's considered a weak field ligand, but it's kind of in the middle. It's not supremely weak, so it's probably not going to be absorbing the low energy range red. It's probably going to be more in the yellowish green range that it's going to be absorbing. So I'll put, if you look at that, spectrochemical series that I gave you with the wavelengths, so that's probably absorbing yellow-green range somewhere in there. Right? It's more on the weak field, but not on the far end. So it's not going to be red on the far end. That would be like the bromo and the iodo, things like that. So red, orange, kind of the next step over there, the fluoro, those kinds of things, the hydroxo. Yellow, now we're starting to get towards the water. So water's right about the yellow-green region if you look back on the prior board that I did with that spectrochemical series with the Roy G. Biv reversed underneath it. So that's my guess. So let's draw the crystal field splitting. Let's pop that up. So this is octahedral, so we're going to get the dz squared here, the dx squared minus y squared there. It's not a supremely huge crystal field splitting, so let's just go like this. Do the dxy, dyz, dxz. Doesn't matter what order you do those in. They're all degenerate on the lower level. Same with this. You could flip those two. We've got our crystal field splitting here. And that's, we said, about, let's see, 750, 700, 650, about 600 nanometer-ish. 550 to 600 nanometer range, give or take. And let's put our electrons in. So we've got 7 electrons. 1, 2, 3. Fairly weak field. So the pairing energy is going to be greater than the crystal field splitting. So it's going to go 1, 2, 3, 4, 5, 6, 7. So that'd be paramagnetic. And what happens is that photon comes in. No idea what a photon looks like. Let's say that's my photon. Ha ha. Here comes my photon. Wah, 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 wah. Bam! Hits this electron right here. Let's make that red. That promotes up, right, into a higher level. That's absorbed. And it will absorb right around that 550 to 600 nanometer range. So if it's absorbing yellow-green, you don't really need this per se, but it's absorbing yellow-green. Let's see if we can get a rough idea of what color that's going to be. All right. So here's that color wheel we did. So if it's absorbing, this would be for additive. This is subtractive. So if it's absorbing yellow greenish, it's going to be, the complementary color would be in the magenta, pinkish magenta range, right? So it's absorbing here, You're going to see blue absorbing here. You're going to see here. So if it's kind of a mixture here, you're going to get in this region. So a magenta-ish, pinkish color, okay? That would be my rough, I mean, give or take, right? There's a lot of leeway going on here. But I would say a cobalt 2 nitrate solution would probably be a magenta-ish pink. Most people wouldn't, so that's magenta. They, you know, was like, what the heck is magenta? So they say maybe a dark pinkish solution. Too bad I don't have one with me because I'm not in my lab right now. It'd be really interesting to go Google that or something, so what a cobalt 2 nitrate solution looks like. I should have brought a jar home with me and we could have looked at it. That would have been pretty cool. But that'd be my guess. Hopefully I'm right. Let's do one more. All right, last problem, gang. So explain why this species was emerald green. This is what, if you were in my class, remember that compound you made, that beautiful emerald green crystals, right? If you did the empirical formula, you got this. So it was the tris oxalato ferrate 3, potassium tris oxalato ferrate 3 trihydrate. All right, I just gave you the oxidation number on the iron. So take a second, pause it, give me the coordination number, oxidation number, all that fun stuff. And I'm actually going to draw the geometry of this. We haven't drawn one with a, the oxalate is a bidentate ligand. Right? I want to draw that for you real quick. So try to do this while I draw the picture up on the board, and we'll take a look at this and then try to predict. Well, not predict, but say, why is it greenish? This board is pretty crazy, my friends. You ready? We've got 3 oxalates, but the oxalate is bidentate times 3 would be a coordination number of 6. So that's going to be octahedral. Happens a lot, huh? And this is what it looks like, right? So the octahedral, you got them up in the Z, Y, and X axis with the iron plus 3. Remember the oxalate, the C2O42 minus, and oxygen connects at one site here and another site there. That's why it's bidentate. Boom, boom. And then this oxalate's bidentate, and this oxalate's bidentate. So you got them wrapping around, but even though you only got 3 ligands, they connect in 6 total spaces. So that's why that's a coordination number of 6. Right? The iron is a plus 3. Why is that? Well, if we look at the complex ion, let's get rid of the potassium. Now, can you see the 3 potassiums, right? Well, that's a positive 3. That means the complex ion is a negative 3. So if I write the complex ion, that's going to have a negative 3 charge. The potassium ions just create electrical balance in the core. That's a coordination compound. And the trihydrate has nothing to do. It's just a hydrated compound. So oxalate's a minus 2, right? So we've got the C2O4 2. Well, let's do that down here. So this is our ligand, C2O4 2 minus. See the 2 minus charge on the oxalate? I've got 3 oxalates at minus 2 each. That's a total of minus 6. So iron minus 6 should be minus 3. So iron has to be a plus 3. 3 minus 6 is a minus 3. That's why it has an overall minus 3 charge on that complex ion. All right, how many d electrons? So here's iron. Look on your periodic table. Iron is an argon 4s2 3d6. If you look on your periodic table, let me double check that. 1, 2, 3, 4, 5, 6. Yep. We're losing 3 electrons. So we're going to lose the 4s electrons first. So there's 1, 2. And then this spin down electron for 3. So we lose those 3. That's gone. Those 2 are gone. That's gone. Leaves us with a very preferentially half-filled 3D subshell with all spin up electrons, unpaired. Iron loves the plus 3 there. So we got 5 3D electrons. Not necessary to do this problem, but I'll go ahead and draw the splitting anyway after we're done. And so the oxalate, if you look on the spectrochemical series, that's weak. That's a weak field ligand. It's actually weaker than water was in the prior problem. So this is actually going to create a crystal field splitting where it's going to absorb even lower energy. So if water was absorbing in the yellowish green region, this is probably going to be down in the reddish orange region that it's going to be absorbing. So let's draw the crystal field splitting, show the electron, popping from the lower to the higher d energies, d orbital energies. Not necessary to do the problem, but let's pop that out. Let's polish this chapter off with some fun in the sun at the end. You ready? So did you do your crystal field splitting for an octahedral complex? You got your dz squared, dx squared minus y squared on top, dxy, dxz, dyz on the bottom. Very small crystal field splitting because of the very weak field oxalate ligand. So the pairing energy is going to be a lot greater than the crystal field splitting. So when we put our 5 electrons in, we get the 3 here, and the next 2 will go up. So it's very, very paramagnetic. Photon comes in, hits that electron, gets absorbed up to an excited state up here, pops it up here. That energy difference should equal the photon energy. And if you look at the spectrochemical series, oxalate's way at the end, not as bad as the halides, but it's way down there, way, way further than water. So that's probably going to absorb in the 650, 700 nanometer range, give or take, which is probably going to be in your reddish-orange region. So it's absorbing reddish-orange, which means everything else will, and this is a solid, it absorbs reddish-orange, reflects off. We see the rest of the wavelengths combined, which is the complementary color. So let's look again at our color wheel with our subtractive color mixing right here. High tech, baby. Okay, so if it's absorbing in the reddish-orange region, right, there's red, reddish-orange going to be right about in here. Complementary color is going to be in the kind of the greenish, the edge of the greenish cyan range, right about there. So it absorbs in here, you're going to see over here. So I'd say the complementary color would be kind of the greenish cyan region. And as you saw in lab, it was kind of a deep green color, kind of cool looking. So we're pretty close on that one, which works. So same process every time, my friends. We're done with this chapter on complex ions. Rock on. Do your extra credit homework, my friends.